Hello everyone, I'm Chen Zhenyu, a PhD student at Imperial College London. Today I'm going to present on temporal consistency checks to detect LiDAR spoofing attacks, which is a joint work with Zhongyuan Hao and Soteris Dimitrian. The first section is the introduction. LiDAR, which stands for Light Detection and Ranging, uses laser to measure the distances between the scanner and objects. Measured distances, along with the firing angle of each laser beam, can be used to calculate 3D coordinates of the object. LiDAR-based detectors will then take a 3D point cloud as input and generate bounding boxes for objects in the environment, providing spatial awareness and enabling the autonomous vehicle to make safe navigation and control decisions. Unfortunately, recent work has demonstrated the feasibility of LiDAR sensor spoofing attacks. Such attacks are able to force 3D object detectors to erroneously output bounding boxes for non-present obstacles. This was shown to have hazardous consequences on driving decisions of end-to-end LiDAR-based perception pipelines. Indeed, in the last couple of years, there have been works that study different strategies to mitigate such attacks on LiDAR-based perception systems. Cao proposed two strategies, CALO and SVF, which leverage physical features to detect spoofed objects. Hao introduced the notion of 3D shadow for genuine objects as a physical invariant to detect spoofed objects. However, current works only leverage static information in a single frame of a target scene. Recently, Cao has demonstrated that it is possible to perform temporal attacks. However, it remains unclear if the current defenses are able to defend against such temporal attacks, which demonstrates a need for complementary approaches. We assume that the object motion should be consistent across consecutive 3D LiDAR scenes, and this temporal consistency would be disturbed when an adversary introduces a fake object. We propose a general and modular methodology, 3D object detection temporal consistency check, for detecting such abnormalities. Our work is the first to leverage temporal consistency to detect 3D anomalies. The second section is a 3D TC2. We adapted state-of-the-art threat model as follows. Number of spoofed points is no more than 200 points. We target on three types of spoofed objects: vehicles, pedestrians, and cyclists. The adversary can perform white box model level attacks and spoof from near objects. 3D TC2 consists of three phases. The prediction phase consists of two modular components, object detector and object motion predictor. The two components work in parallel. The output of the two components in the prediction phase are then aligned into a common representation. After the alignment, we can analyze the results to indicate a potential LiDAR spoofing attack. To demonstrate the application of our proposed methodology, we implemented a prototype based on 3D TC2 for detecting ghost objects. The components used in our implementation are summarized in this table. The object detection modules, point pillars and seconds, take in the 3D point cloud at the current frame and provide 3D bounding boxes of objects relatively to the aggro vehicle. Object motion prediction module, MotionNet, takes a sequence of historical 3D point clouds as input and outputs a bird's-eye view map of the predicted frame in the current time step. Instead of predicting bounding boxes, MotionNet predicts for each grid cell the object class label and motion information. In the alignment operation, 3D bounding boxes are reduced to a 2D planar representation, which is then mapped onto the MotionNet bird's view map. In this way, the bounding boxes are aligned with the grid cells. For the comparison, we devise an experiment with a simple cell match counting strategy. The object category that has the most cells in the bounding box region would be considered as the predicted object, and if this object category differs from the object detection result, it is marked as a potential LiDAR spoofing attack. The next is the experiment and results section. We use the mini dataset from nuisance, which contains 3D point clouds of 10 driving scenes. Each driving scene is a recording of approximately 20 seconds, with a sampling rate of 2 Hz. For the whole dataset, there are 39, 35 frames and 404 keyframes. For our implementation, the alignment operation is evaluated to answer the following design questions. Question 1. Is MotionNet an appropriate choice for object motion prediction? Question 2. How accurate is the transformation and alignment process of 3D TC2? For a given object category, we define the match ratio as the ratio of number of cells with that object category over the total number of cells occupied by all bounding boxes of that object category. The match ratios are summarized in this table, where from near refers to objects in front of the aerial vehicle up to a distance of 8 meters from the LiDAR unit, and from far refers to objects further than 8 meters. We observed that over 80% of the cells with the vehicle category fall inside the vehicle bounding boxes, demonstrating both a good prediction match and alignment. A lower match ratio score obtained for pedestrian objects is due to that bounding boxes occupy much larger areas than the combined cells with predicted pedestrian categories. For cyclists, the limited training data resulted in poor detection and prediction performance, consequently resulting in poor match. As for other object categories, we observed higher match in front-near regions compared to the further regions. Our evaluation indicates that the design choices of the use of MotionNet and the bounding box transformation are suitable for bigger objects in our implementation. As for smaller objects such as cyclists, we might need a stronger prediction module. For attack detection module, we have the following design question to answer. How effective is the cell match counting strategy for performing a temporal consistency check to detect module-level LiDAR spoofing attacks? We generate an adversarial dataset by injecting a spoofed object into each of the 362 keyframes in the original dataset at a location of approximately 8 meters in front of the vehicle. We define the attack success rate as the ratio of all successfully detected spoofed objects over the total number of spoofed objects. The detection success rate is the ratio of all successfully identified spoofed objects over the total number of successfully spoofed objects. Recall measures how well the detector is able to correctly identify spoofed and genuine objects. As shown in this table, Our implementation of 3D-TC2 is able to detect spoofed vehicle objects with an accuracy of more than 98% and detection recall over 91% for both detectors. The poor detection performance for smaller objects could be attributed to MotionNet's inherent significantly poorer object classification. In all, our implementation of 3D-TC2 is useful and capable of detecting spoofed objects with high success rate. Our approach with 98% detection rate for spoofed vehicle objects performs better than state-of-the-art defenses. For ghost objects that we fail to detect, we observed that MotionNet also erroneously outputs cells to support ghost bounding boxes. This can be fixed by exploring a stronger comparison strategy. To answer how efficient is the implementation of 3D-TC2, we measure the runtime on a machine equipped with an i7 processor, 62 GB RAM, and 2 GB GPU. From the runtime breakdown, we see that the inference or prediction time of the modules take up the majority of the total runtime. The additional overhead introduced by our approach is approximately 5 milliseconds, which is a good trade-off in providing verification of spoofed objects. The overall runtime of 41 Hz demonstrates that the implementation of 3D-TC2 is able to provide real-time detection. We also expect 3D-TC2 to be able to detect temporal anomalies of hiding attacks, which aim to hide objects from detection. However, if the hiding object is temporally consistent, this approach might fail. As 3D-TC2 is not perfect, there could be instances where it fails to detect or erroneously detect spoofed vehicles. In these instances, the autonomous vehicle should take a safety-first approach and prevent collision. 3D-TC2 can also be used in an offline fashion as a forensic tool for post-incident analysis of 3D point clouds for spoofed objects. The last section is conclusion and future work. We propose the 3D-TC2 that uses motion as a physical invariant to detect temporal inconsistencies between detected 3D objects and expected 3D objects in LiDAR-based perception systems. We implemented a prototype of 3D-TC2 and showed that it can detect spoofed vehicle objects with a good performance. In future work, we intend to explore alternative approaches for motion prediction, alternative sequence modules, and new attack detection strategies suitable for smaller objects. We also consider a stronger adversary that performs temporal attacks and study the robustness of the 3D-TC2 to such attacks. Thanks a lot.